Alright, hi everybody. Welcome to our video on the unit circle. Alright, so this lesson is probably one of the most important lessons in our course, and it's the very first one, so it really is going to set the stage for a lot of the really key ideas from trigonometry. And it's going to be a little bit long because I really want to derive everything so that you know what everything means and where everything comes from. Now, we started this lesson in class, so you can see that there's already some of the notes filled in. If you weren't here in class on Monday, don't worry, you can kind of catch up on these things. So I'm going to do a quick summary of the things we've reviewed. All right, so let's start with what is a degree versus what is a radian. So whenever we talk about degrees, so a degree is going to be defined as follows. 1 degree, and we put that little circle symbol, is literally 1/360th of a turn along a circle. So if you take a circle and you cut it up into 360 equal pieces, 1 degree would be one little tiny slice. All right, so based off of that definition, if 360 degrees is 1 full turn, then half of that is half a turn, which is 180. So that's why a straight angle, we call that 180 degrees. So that's where that comes from. And of course, there's many other special angles we can build from that. So if we cut 360 into 4 equal pieces, 1/4 of that is going to give us 90 degrees, which of course we call that a right angle. All right. Now, when we talk about radians, what is a radian? I'll remind you, it's a real number. So a real number, remember we have our number line over here, and you can see it pictured on the iPad here. If we have a real number that's positive, we go start at 0 and move to the right. Okay, so for a radian, what I want you to think about this is I like to call it the wet noodle because it's something that sticks in your head here. Imagine that orange piece of a line segment is a wet noodle, so it can wiggle around, it's soft. As we wrap it around the unit circle, notice that that unit 1 that's straight gets bent. So it actually, if you kind of go from here, notice that it doesn't get all the way to the y-axis, right? It stops a little short because of the bending around the unit circle. Okay, so literally 1 radian is basically about this length, and then you can always kind of check the stuff out with a calculator in more detail later. But for now, that's really all I want to review in terms of radian versus degree. In some sense, they're trying to get at the same thing. It's trying to basically describe an angle. Now, the way I've defined a degree, I've kind of introduced the circle as well. But if you remember in 110A, you actually, or in your first pre-calculus, we talked about angles as basically 2 lines that meet. So there's a little bit of a kind of a connection here, but let's remove that for now. Okay, another thing I want you to just remember and have on maybe a formula sheet would be these 2 special triangles, the 30, 60, 90 and the 45, 45, 90. So I've basically chosen side length so that this short side is 1, the long leg would be √3, square root of 3, and then the long side is 2, hypotenuse. Okay, for this 45, 45, 90 triangle, so that's isosceles, since these are both the same angle, then these 2 sides, if I call them unit 1, then the hypotenuse is square root of 2. All right, so I won't review all of these trig functions, but remember that in the previous part of the course, you actually define them using a reference triangle. So we would call this the reference triangle. And once we have this triangle and we know the 3 different sides, and we know this angle theta here, well, we can define sine of theta to be opposite over hypotenuse. This is the opposite side, the hypotenuse is this long side, and etc. I won't go through each of these definitions, but essentially they're built from ratios. Remember, ratio is just a fancy term for fraction. All right. Most important theorem in all of mathematics. Let's put even some extra stars here. Really emphasize the importance here. And I'll even put most important. theorem in all of math. So quite the declaration. I think it's true. Now what the theorem actually tells us is it tells us that if we have a right triangle, so here is the right angle, and if we label the three side lengths as length A, length B, and length C, then the relationship between these triangles is that the square of this leg plus the square of this leg, a squared plus b squared, is equal to the square of c. Now, if you look at this picture over here, this is, remember, when you square a number, it's visualized as the area of a literal square. That's why you see this red square over here. That would correspond, in our picture, it's the second longest one, so maybe A over here. And then this black square would be the shorter side. It looks like it's B on our picture. So maybe one way to visualize it is you'd have like A squared, B squared, and then C is the bigger one, C squared. Which is kind of surprising, since if you look at my picture, it looks like A squared plus B squared looks bigger, but it's not. You can actually prove that they would be the same. And in fact, in our Canvas course, I linked to a visual proof of this, which is different than this picture here. This is an entire proof, but it's very little words here, but it's very beautiful. I love that picture. You can see it all over our Canvas page. But again, we're going to talk about this theorem all of the time. And in fact, pretty much you'll see me reference this in almost every lecture since it's so important. All right, so let's go back to this unit circle here. So remember, if we start with a unit circle, what is that? That is a circle of radius 1, and we're going to center it at 0, 0 on our Cartesian plane. So that's if I label the x-axis and the y-axis. All right, so the equation right here that I have highlighted really just comes from the Pythagorean theorem, and you can see this little, let me zoom in a bit. If you look at the coordinate x comma y, so that's this red point right here. Let me make it really thick so that you can kind of think about it. It's the point on the circle. Okay, well, literally, if it has coordinates x and y, that means that this length down here, right below it, will be x. This vertical distance will be y. And then because it's on the unit circle, the hypotenuse is actually length 1. Apply the Pythagorean theorem, and it tells us that x squared plus y squared is equal to 1 squared, which is exactly this equation. So that's why we think of this as the definition of the unit circle, because any point x, y, if it is on the circle, it will have to satisfy that equation. All right, cool. So now that we've got that, I'm going to skip this example. Basically, it just verifies that this point 1/2 square root 3 over 2 actually lives on the circle. Let's put this little check mark since we checked this. If you didn't do this calculation earlier, just pause the video, see if you can just read the notes. Essentially, all we do is the x-coordinate is 1/2, the y-coordinate, and then we just plug them in to this equation. And of course, if it is on the circle, we'll get that this equation is true. Let's maybe even emphasize that, put true here. Check mark. Okay. This next point, x comma negative 1/5, we don't know the x-coordinate, but we are told that it is on the unit circle, and it's also in quadrant 4. So quadrant 4 is this zone over here. Quadrant 1 starts up here. Quadrant 2 is here. Quadrant 3 and quadrant 4. Okay, so if this point is on the unit circle, then basically we get this equation here. And notice that the x, I just kind of wrote it as x because I don't know what it is, but I can replace the y with negative 1/5. And in fact, we can solve this equation to get that x is equal to plus or minus the square root of 24 over 25. In class, I was talking about some calculator tricks. I'll bring up calculator tricks a little later again. And then if we simplify, remember that whenever you do a square root, you have two options from algebra. Now, we're actually going to pick the positive one. Why do we pick the positive one? Well, because we have extra information. We want this to be in quadrant 4. So the x values, if you think about it, right, all of this side is positive x values. So that side of the unit circle has x is positive. Okay, fantastic. Let's talk about terminal points next. So this is really fundamental principle here. And it's going to be basically the building block between a radian, which is a real number, and an angle, which, remember, angles are kind of two sticks. So to do that, we're going to talk about a terminal point. Now, my preliminary definition is I like to call it the wet noodle, where if you take the real line, now right now it's covered up, but if you imagine it as just being kind of orange, since you want to imagine it as wet. So if you cook pasta, it gets wiggly, so you can kind of bend it around and stuff. So it starts straight, but you can bend it. So if you kind of see in this picture, I've kind of wrapped it around in kind of a coil. Now I'm trying to wrap it around so that it basically would lay on top of a circle perfectly, of course, if I could do this. And as I keep wrapping it around, I would get this kind of taller and taller circular pasta stack. Keep that image in mind as you think about radians, because it's really helpful. Now, the definition we're going to say is okay, well, we're going to start all points at 1, 0, just because we have to pick a specific point on the unit circle. And then 1, 0 is going to correspond to the 0 in the real number. So that's kind of an association that we make. Now, as the t value, so if t is positive, imagine this purple length, whatever that is. What we're going to do is, if you think of it as a wet noodle, you can literally wrap it around the circle. And if it's positive, we're going to wrap it around in the counterclockwise direction. So that's up. Okay, and then wherever we end up, so if t is a specific distance, the final point, that is what we're going to call the terminal point. So this is, so sometimes I like to draw these eyeballs to kind of say like, hey, look at that. That's a really key idea. All right, cool. So counterclockwise for positive numbers, and then if we're going to go negative, so we have this pink distance, we wrap it around underneath in the clockwise direction. All right, now of course, the real line is really, really long. So if the number is really long, maybe like 5 times the length of the circle, you can see that you'd wrap around it many, many times. Okay, now the consequence of that is that if you wrap around it many, many times, you're kind of landing at the same point over and over again, because again, as you wrap over the circle, you're just kind of covering the same ground again. So, all right, but let's move on from now. Now, what we want to do is we want to kind of think about real numbers and radians and connect that to specific locations on the unit circle. Now, to do that, we're going to start with this definition of pi. So pi is actually not really a number, it's more of a concept. It's the concept of the ratio of the circumference of a circle, because remember, circumference is the entire length of the outside of a circle divided by its diameter. Okay, so it's the pi is defined as the circumference divided by the diameter. Now, if you remember, the diameter is just 2 times the radius. Just I'll remind you, radius is this part here. Radius is one of them. Here's the second one. So the diameter is just 2r. Okay, so because of that, we can actually just rewrite this formula as the circumference is 2 times pi times r. You might remember that formula from your previous courses. But really, this is fundamentally important in all of mathematics. So pi is one of those really important concepts. So, and we're already seeing, like, some of the best things in math in just this lesson. All right, so this gives us the connection to radians. Now check this out. So we already did this in class, but let's review it. I wrote 0 equals 2 pi to represent that if I start at 0, remember 0, we start at this point down here. And if I do one full turn, that length when I end up at the same point that I started with, because remember, the final output, that's what we call terminal point. And if I do the full circle, that is just 2 pi. Because I'm on the unit circle, if I plug in 1 for r, the entire circumference is 2 pi. So that has some really interesting consequences. Even though I ended up where I started, we now know the full length is 2 pi. So if I cut that in half, then I know that half of a full turn is this red part up top would just be pi. Okay, so and then we can talk about these terminal points. If I have t is 2 pi, I start at 1, 0, but then I do a full turn, I end up exactly where I started, I'll get my terminal point will have 1, 0 coordinates. Pi, I'll end up only halfway, which this coordinates, of course, are going to be negative 1, 0. So I divided it by 2, because that was an easy number to divide 2 pi. So why don't we cut it up in half again? So if I take pi, divide it by 2, I get pi over 2. So I just write that symbolically. Now notice that that just means I land up here. So essentially pi over 2 corresponds to 1/4 of a turn of my circle. So, you know, it's a little bit unfortunate that half of a circle is pi and then 1/4 is pi over 2. I feel like those numbers are a little bit off, but you don't have me to blame for that. Okay, now, of course, if I do pi over 2 as this blue, from 0 all the way up here, pi over 2, the coordinates of this are just 0, 1. So that's easy to figure out. And then the third number that's easy to figure out is 3 pi over 2. So the way to think about it is, let me do it really bold in purple, and I'll delete that in a second. You can think of this as basically this purple part. If I do half the circle, that's pi. And the only distance that I'm missing is this arc here. But we already know from earlier that is pi over 2. So if I take pi, add pi over 2, do some quick algebra, I get 3 pi over 2. And of course, what are the coordinates of 3 pi over 2? Well, 0, negative 1, because the y coordinate is negative 1. So there you have it. You have the kind of the 4 important easy points on the unit circle, and now we know what the angles that correspond to these are. Key one is 2 pi, pi, pi over 2, and 3 pi over 2. All right, and then I'll skip over this example since we already did it, and it's kind of easy. You can just kind of pause the video, check your answers, make sure that you get the same points here. I will, so I haven't introduced this yet, but if you ever see this little triangle with the squiggly line, so this is very French. If you are ever driving in France in the mountains, you'll see these signs, and what they represent is a dangerous curve. So if you've ever driven in mountains, you know that the roads are very small, and you know they can get dangerous with rock sliding and stuff. So I use that as a kind of a warning. Something kind of tricky is happening. So just keep that in mind. Now, what is the notice here? It just says that different t values can have the same terminal point p, right? T is 7 pi means I just wrap around this, well, let's see, I don't wrap around it 7 times. I just basically do 7 half turns. So that's going to be 3 full wraparounds, and then I'll end up at negative 1, 0. Now, of course, I ended up over here. I'm just doing some stylistic just so that you can count the number of wraps. Negative 3 pi is I'm going to do 3 half turns, 1, 2, 3, but in the negative direction. And notice I end up at the same location. This is something that we're going to encounter, so that's what makes trigonometry a little bit challenging. All right, and finally, negative pi over 2, because remember, if we have a negative number, by convention, we're going to go down instead of up. Now, if pi over 2 was going 1/4 of the turn up, negative pi over 2 is still 1/4 of a turn, but we just go down. Sweet. All right, so pretty much that's the terminal point. So next in class, we pretty much got to this point. So this is the next really big theorem. So what does it say? It says that the terminal point for pi over 4 is p with coordinates root 2 over 2, comma, root 2 over 2. So what is pi over 4? So if you remember our picture, let's just go up to the previous picture here. Pi over 2 was this blue. It was half, well, I guess let's say it's a quarter of a circle. If I cut that in half, then I have pi over 4 is right here in the middle of the blue part. This is going to be 1/8 of a circle. So I will not repeat the proof. So if you weren't in class, you can pause the video here and copy it down. But the key idea was that this point, pi over 4, is really special, and it has to land on the line y equal to x. Notice that the final answer was the same value for x and the same value for y. And that's the kind of the key to the proof here, and I'll let you read the notes if you didn't see it earlier. Okay, one more thing I actually added after class was this little tiny square. The square I like to add just means it's the end of the proof. I actually had it typed out the start here, and then here's the little end. You know, it's just math convention. I really like it. All right, so let's do this next problem together. So we didn't do that in class, so this is new stuff here. I encourage you to pause the video and see if you can just figure out what these are before I give you the solution. Okay, hopefully you've paused it and you tried to solve them. So let's see, how can we figure it out? So I added this little pi over 4 trick. Let's talk about this real quick. So this is something I invented just to kind of help us visualize what's going on. So I was using green for pi over 4. So remember, pi over 4 is 1/8 of a turn of a circle. Look what happens. If I do 2 pi over 4, so 2 times pi over 4, notice that we have that the 2's cancel and it'll give us pi over 2, which of course makes sense just from our geometric definition, right? If I take pi over 4 and I double it, I'm back to pi over 2. I already knew that, but it's good to kind of confirm it this way. If I times it by 3, that doesn't simplify, so I just get 3 pi over 4. So this kind of gives us the next important new spot. Now remember what this means. This means if I measure from here all the way to the beginning point, that has distance or length 3 pi over 4. So if I were to stretch it out and put it on the real number line, 3 times pi divided by 4, that's the length on a real number line. But of course, represented on the circle, it looks over here. Now, what if we do 4 times pi over 4? A little bit of algebra tells us that we should get pi. Okay, and we do. We get this now. The reason I call this the pi over 4 trick is I want you to think about it in a certain way. So always draw a quick little unit circle, and then pi over 4, you just should remember it's the one that's halfway between the axes. And then if you do 2 of them, you land over here, and then you do the halfway mark, you're at 3 pi over 4. The next one, you're going to be at pi. The next one, and I'm not even going to do the algebra, but check it out. We can just count the whiskers. I call these whiskers, by the way. 1, 2, 3, 4, 5 pi over 4. 6 pi over 4. Check this out. Notice 6 pi over 4 simplifies to 3 pi over 2, which we knew it was 3 pi over 2 from previously. And then the last one will be 7 pi over 4. So one more time, what is the pi over 4 trick? It's really this. If I start with a quick little sketch of a unit circle, I just basically do these markings, and then I count. So I count 1 pi over 4, 2 pi over 4, 3 pi over 4, 4, 5, 6, 7, 8 pi over 4. And notice that the very last one, 8 pi over 4, is the same as 2 pi. So it's one of these kind of handy things that as you get practice, you can get pretty fast at graphing. All right, So here we go. Our question asks us to find the terminal point on the unit circle determined by t. All right, so here's our t, 3 pi over 4. So if we do the little whisker trick, 1, 2, 3 pi over 4, we know we're going to end up right here. Okay, so what are the coordinates? So remember, we know that pi over 4 has root 2 over 2. And now the beauty of just using these whiskers is that basically these 4 points all are going to have the same numbers. The only difference is going to be which ones are positive, which ones are negative. So if you look at this picture here, now let me see if I can draw something kind of cool here, kind of helpful. Notice that if I go straight down, the x coordinates are the same, but the y coordinates are different. One's positive, one's negative. Here, if I do my whiskers, the x coordinates are the same, but my y's are different. So basically, I can draw this green square because all of those distances are the same. They're just root 2 over 2. All right, finally, what is our answer here? We notice that the x-coordinate is negative, so I'm going to make this a negative root 2 over 2. The y-coordinate is positive. So there is our terminal point. Let's move it. I don't know where to put it. Let's put it maybe down here. I don't know why I chose red. Let's maybe color it like this. And I'll use capital P. Now, I don't know if you've noticed, I put these little sticks on my P's. This is just to signify that this is a capital P. Because especially when you're writing without lines, how do you know which one's capital? Is this lowercase or capital? So I put a little stick there to kind of indicate that. And sometimes I put the little stick here to indicate this is a lowercase. Anyways, it's just my own writing conventions to kind of help clarify things. Okay, cool. Here is our terminal point for our first question. Now for part B, it says negative 7 pi over 4. So let's do quick whiskers and then let's count. And we're doing it negative. So we're going to go negative 1, negative 2. Actually, it's probably easier if I don't try to draw it, but just kind of count with me. 1, 2, 3, 4, 5, 6, 7. So we actually end up over here. We went this way, but check that we basically counted 4 whiskers. 7 whiskers of pi over 4. 1, 2, 3, 4, 5, 6, 7. Remember to count the axes because those are at pi over 4s as well. All right, so that's where we land if we do negative 7 pi over 4. And the terminal point, well, this one's easy. It's the same as pi over 4. So if, by the theorem we covered earlier, that's going to be root 2 over 2, both of them positive because I'm in quadrant 1. Okay, hopefully if you got the same answers as me, fantastic. You're doing great. All right, cool. What's next? Let's take a look. So for the next part, if you need a break, now would be a good time to just take a break, pause the video. I'll be here as soon as you come back. All right, welcome back. So here is basically the last really important theorem, and from this we'll be able to fill out the entire unit circle. So I've already kind of pre-written the proof so that we can go a little quickly. And it says, what is the terminal point for pi over 6? And actually, this is kind of a fun theorem because we get two things at the same time. So the same proof gives us both pi over 6 and pi over 3. So, all right, we're going to figure out what these points are going to be, and then we'll write them down at the final answer. Because right now, we have no idea what numbers land at pi over 6. So if you look at this picture right here, pi over 6 is what? So one way to think about that would be, remember pi over 2, I did that in blue, would be a quarter circle. And if I cut that up into 3 equal size pieces, if I divide that by 3, these are all supposed to be equally the same length. Well, pi over 2 divided by 3 is pi over 6. So that's one way to think about it geometrically. But what we want to know is, well, what's the x-coordinate and what's the y-coordinate? We know it's going to be somewhere over here just from the geometry of where we're at. But, okay, so let's delete that blue so that we can kind of study the proof. So if you look at our picture, we have P, which is going to be the terminal point for pi over 6. And I'm just going to refer to this diagram here. You can see pi over 6 in red from our starting point 1, 0 this way. So I'm going to temporarily label these as A and B because I don't know what those numbers are. Okay, now to actually come up with this proof, it requires some kind of really clever imagining. So let's kind of see what happens here. We're actually going to look at Q, which is going to be, oh, I shouldn't have chosen Q. Let's call this something else, R, because pi over 3 is actually going to be up here. But, all right. Okay, caught my own little typo here. All right, but let's see. What do I write here? It says, use the diagram to argue why the distance between P and R. Oh gosh, I already used R in the proof. I'm sorry. Okay. So P to R, so that's this orange distance here. And the distance from P to Q, that's from P going along the red all the way down here to Q, we should argue that these are both the same. Okay, so one way to think about it is, well, we actually know what the distance is from here all the way down, pi over 2. So the orange distance is actually the blue minus the red. And let me actually uncover this part here. So that's going to be pi over 2 minus pi over 6. If we just do some quick algebra, it gives us pi over 3. Okay, so now we know that this orange piece is pi over 3. Okay, now what about from P to Q? Well, this one's pretty easy because from 1, 0 to P, it was pi over 6. But if I go pi over 6 in the negative direction, that's how I get to Q. Well, add those two distances together. Notice I'm adding them because I'm thinking of them as an actual distance, so like a wet noodle here. So in this case, we would do pi over 6 plus pi over 6, also pi over 3. So they're the same, which is not really too obvious until you actually kind of think through it like we just did. Check this out. So next what we're going to do is we're going to simplify it using the distance formula. So we now already know that the distance from P to R, that's from here along the orange to R, is equal to P to Q. Now the other thing that's special is Q, since I'm going in the negative direction, pi over 6, it should have the same exact A coordinate because I'm just basically going in the same distance, just one's up, one's down, but the x coordinate should be the same. But the y coordinate, of course, should just be negative. So this is going to help us. Okay, let's uncover the next part here. Okay, so if I start plugging things in using the distance formula, remember the distance formula is the square root of the difference between the x coordinates plus the difference between the y coordinates. So let's do P and R first. P has x coordinate A minus the x coordinate of R, which is 0. So A minus 0 squared. And then if I have the y coordinates is going to be B minus 1. And I have square root. Now, what's the distance between P and Q? So the difference between the x coordinates is going to be A minus A. That's going to be A minus A squared. Plus, now I do B minus a negative B. 2 minuses actually gives me a plus, so I'm going to get B plus B squared. So the next trick is, okay, now that I have this, because I have square roots on both sides of the equation, I can actually go ahead and just square both sides to get rid of the square root. And I get A minus 0 squared is A squared, b minus 1 squared doesn't really simplify, so I'm just going to write it down. A minus a disappears, it's 0. B plus b, I can write that as 2b squared. Okay, well, we have a little bit of algebra to do, but that's not too intimidating. Let's actually ditch the picture and follow the little arrow to the next part of the proof. So from here, what are we going to do? So here's the original equation. A squared plus b minus 1 quantity squared equals 2b quantity squared. All right, well, if I use my exponent rules, I'll distribute the squared to the 2 and the b. I can write that as 2 squared, which is 4, and then b squared. Okay, now I just moved the b minus 1 squared to the other side. And notice that 4b squared stayed here, but if I move this to the other side, I picked up a minus sign. Okay, so I basically isolated the a squared. So keep that equation in mind. So we're now ready for the next step. So that was step 1. So we got this kind of important equation. We're not done because the goal is to figure out what a is and what b is. But notice that so far I never used anything about the unit circle. So now we're actually going to say, well, p is on the unit circle, so we actually get an extra equation. We have this equation, it's true, but a squared plus b squared has to equal 1 is an extra equation. So let's see what we can do. So basically, remember here we solved for a squared? So if I just replace anywhere I see a squared with this more complicated thing, we can actually go over here. So notice this is a squared. I just replaced it with that big formula. A squared plus b squared has to equal 1 by the fact that it's on the unit circle. And now, magically, there's no more a's. I basically got rid of them. So I have a little bit more algebra ahead of me, but I can do 4b squared plus b squared gives me 5b squared. Now, this next part, I think it would be fun if you actually pause the video and try to do it on your own. So see if you can simplify this for b, but let's check it out together. Okay, basically just expand, collect like terms. At this point, let's just kind of skip ahead and look at this piece here. It looks like a quadratic equation. Now, of course, there's many ways to solve a quadratic equation. If you're lucky, it factors. And in fact, notice that we have a 4, 2, and a negative 2. So if I just divide by 2, I can simplify it. And then, of course, if we're lucky, it factors. And we are lucky. We can use 2b minus 1 times b plus 1. So we are making some good progress here. So let's see. Let's uncover the next part. Once you've got this factored as a product of two pieces, we know, well, 2b minus 1 is equal to 0, or b plus 1 has to equal 0. One of those two has to equal 0. So this is telling us that b is equal to negative 1. And I crossed it out. Why did I cross it out? Let's go back to our picture. Remember, b is supposed to be the y-coordinate of what we would get as the terminal point if we stopped at pi over 6 in the positive direction. So we already know, even before the calculation, that the b has to be positive, so I can basically eliminate this root. Solving the other equation gives me that b is 1/2. Sweet. So we got b is 1/2. That is great. We've actually solved for one of the numbers. We now know b is 1/2. But of course, if we look at this equation, that star, I can plug in 1/2 on everything on the right side. The only thing that's left is the a squared, so we can actually solve for that, or we can actually just solve for it. What happened to my 1/2 here? 1/2. Or we can just plug it into the equation of the unit circle. I guess this is easier. And just solve for a. And we'll get Square root of 3/4 plus or minus. Keep in mind, where are we? A is supposed to be the specific number that's the positive one. So square root of 3 doesn't simplify, but square root of 4 does. So bada bing, bada boom, we get our second value. A is root 3 over 2. Cool. So now we know what the terminal points are for pi over 6. We actually got b first. We solved that this had to be 1/2. And then we solved for a second, which was square root of 3 over 2. Super important. And I know this might be very long. Not every lesson is going to be this intense and with a lot of equations. But this is just, again, the most fundamental lesson for trigonometry. And I think it's really cool. When I was a student, my teacher just kind of was like, here's a unit circle, let's move on. And I never felt comfortable with it because I didn't know where everything came from. So I really hope this, even though you don't need to memorize every little step here, I hope just watching me develop the theory was pretty fun. Okay, one more thing to do. We want to know what pi over 3 is. So check this out. Let me actually show you the argument real quick over here. Remember how I said that if we cut up, remember this was pi over 2, 1/4, let's actually do it in blue, pi over 2 is that. And if I cut this up into 3 equal pieces, okay, I'm just trying to do it visually here, that roughly looks correct, right? 3 equal pieces of the blue part. Well, pi over 2 divided by 3 is pi over 6. And if I add pi over 6 plus pi over 6, that should give me this number, which is pi over 3, right? Let's just do that calculation off to the side. Pi over 6 plus pi over 6 is 2 pi over 6. Canceling the 2 from the top and bottom gives me a pi over 3. So pi over 6, 2 pi over 6, 3 pi over 6, 3 pi over 6 would give us pi over 2 after canceling. All right, cool. Now, we actually know the coordinates of pi over 6 are root 3 over 2 and 1/2. Here's the final magic trick in this section. And I didn't draw pi over 4 just because I'm trying to keep the picture clean. But if you remember the line y equals x, pi over 4 is actually on that line. And because of the symmetry of how I did everything, because I'm taking pi over 2 and cutting it into thirds, this distance from, let me color code this, the distance from here to here is going to be the same as the distance from the line y equals x to pi over 6. So those are the same, which means if you remember your symmetry, if you have points that are symmetrical across the line y equals to x, do you remember the trick? You actually flip the coordinates. So I don't even have to do anything extra for pi over 3 by just making that beautiful symmetry argument. And now I have that pi over 3, which is kind of confusing. Pi over 3 is actually a bigger angle because it's like further along. Pi over 6 is tinier because I've cut it up. I've cut up pi into smaller pieces. But there we have it. That is the last big angle, because now we had pi over 2, pi over 4. The new ones, pi over 3 and pi over 6. That is all you need for a complete unit circle, and you know where everything comes from, which I think for me is the most important part. Okay, cool. So actually, before we do this next problem, I want to introduce what I call the whisker trick. So this is something I invented when I was a student. Since I didn't get to use cheat sheets, I had to memorize everything. So I came up with something that really helped me. So basically, I start by just drawing the whiskers as best I can to the pi over 4s. We already saw those. And then pi over 3 and pi over 6. Pi over 6 was the smaller angle, and I'm just going to move a little bit down and a little bit up. That's what I call the whiskers, because it's like, if you see a cartoon cat, they have 3 whiskers on each. Okay, I can't do. Just 3 whiskers. Same thing on all of these. I'm going to go up, up, up. So I got the little whiskers. So the way I think of these, and I'm not sure what colors to use, let's maybe use pi over 4s are going to be the blue parts. And let's maybe do orange for the pi over 6s. 1 pi over 6, 2 pi over 6, 3 pi over 6, I'm the same place over here, so I don't need it. And then I'll basically keep making my way through them. And I know they look like they're really close together, but this is literally another pi over 6 in between them. Because remember, we cut them up into 3 equal pieces. All right, and let's label this one original pi over 6, pi over 4. And basically with just this, plus knowing where the location of everything is, if you just know how to kind of hop around, you can get to any location by just kind of counting and drawing a quick little picture. So whenever I took tests, I would just draw these for every single problem. I would just start from scratch because it only takes about 15 seconds to draw it. And then I would just kind of count my little whiskers and then go along my happy way. All right, cool. So before you see me solve this video, why don't you go ahead and pause it? So I'll give you a chance to think about it on your own. Okay, welcome back. Let's go ahead and do this one. So notice we got a 4 pi over 6 and a negative 4 pi over 3. So let's zoom in a little bit and let's give each of these their own little whiskers. All right, and I'm going to copy this for the next problem so I don't have to draw it again. Okay, so zoom in a little bit more. 4 pi over 6. So as I see this, I purposely didn't simplify it just because I want us to do, okay, pi over 6, remember, was this one. Then I'm just going to count 4 of them using pi over 6 as my fundamental kind of angle. 1 pi over 6. 2 pi over 6. 3. 4. There we go. That's where we end. 4 pi over 6. So since we're finding the terminal point, what this ends up basically looking like is, remember, we know the terminal points for pi over 6 and also pi over 3. And if you look at this picture, it's basically going to be a mirror image of pi over 3. So we actually use the pi over 6 for counting purposes, but we're actually going to use the pi over 3 coordinates. So let's see, pi over 3 was 1/2 root 3 over 2. And for 4 pi over 6, the answer is going to be, let's just write it down here. So the x-coordinate is going to be, instead of positive 1/2, it flips to the other side, negative 1/2. And then the y-coordinate is going to stay exactly the same. So that's basically what we're doing. We're using a lot of interesting symmetry arguments because basically I have that the x-coordinates are just one's positive, one's negative, but the y-coordinates are exactly the same. So you're just both going in the positive direction. All right, that is our terminal point for 4 pi over 6. I hope you got that correct. Great job. All right, how about let's move to the next one. Negative 4 pi over 3. So if we're going to use pi over 3 as our fundamental unit, the tricky part is you have to kind of skip over the first couple whiskers because pi over 3 is this kind of furthest one from 0 over here. All right, so there's 1 pi over 3. Now, when you do the whisker trick, you actually hop over, if you're counting by pi over 3s, you would hop to this next one. There's 2 pi over 3. If I'm going to hop over by pi over 3, I'm going to do another pi over 3 over here. There's 3 of them. So notice I'm kind of hopping over in a very special way. From 0 to pi over 3, negative pi over 3 is over here. This is going to be another pi over 3. And then if you're thinking, well, why do I hop over that? Well, let me just remind you. This distance is pi over 6, and this distance is pi over 6. So 2 pi over 6 is pi over 3. That's why you hop over that way if you're hopping by pi over 3s. Okay, here's another pi over 3, and we have one more to hop. Where do we land? We're going to land right here. So there's another negative pi over 3. So our final point is going to be over here, which, if you already did this, you already knew this, but it's actually the exact same coordinates that we got previously. We just got here from a totally different path, different hops. Sweet. Okay. Well, what I would do now is probably take a quick break, maybe get a cup of coffee. When you come back, I really think if you printed this out, you don't need to print out a new one, but notice this is a fully blank unit circle. And notice what I call the little whiskers. Here it's drawn as kind of full lines. So this is, my whiskers are a little easier to draw, but pi over 4 is over here, pi over 6 is a little bit below, and pi over 3 is above. So one of the things you're going to do is, let me just fill out a little bit of it. This is 1 comma 0. And this notation is kind of tricky if you don't know it. Here is for degrees, so it's 0 degrees, but also 0 radians. So this spot is the radian. Let me color code this. Let's maybe do degree in orange. No, choose a different color. Let's do purple. So you do this for all of them. And then maybe I'll do red, the coordinates of the point. So it's kind of, the parentheses are there for you. All right. Let me just do a couple of them. Let's do pi over 4. So pi over 4 kind of has the fraction part. Remember, this is going to be our radian, so I'm going to do it in blue, pi over 4. What are the coordinates? We learned that this was root 2 over 2. Those are coordinates for the terminal point associated to the length pi over 4. Because remember, although I label it there, literally the length pi over 4 is this. And I don't want you to ever forget that connection, because that's the most important part of all of this, is that when we use pi over 4, we're literally talking about the arc length corresponding to the point. Okay, there you go. I'll let you fill out the rest, and you can kind of fill out all the ones with negative coordinates. It's really a great exercise for you to learn the unit circle. Okay, one more thing I want to point out. So actually, give me 1 second. I'm using this new software, which I guess I'm not super good at using it, so I apologize. Let me all right, I think we're rolling again. Is that true? I hope so. All right. Cool. So remember let's go to the modules real quick. So if we go to the handouts, there's this trig game. So if we click on this page here, we can open up this trig game in a new browser, and then we can play this, and this will really help you kind of memorize all the different angles. So right now we'll play what are the angles let's do all of them. All right, negative pi over 4. Okay, pi over 4 is, notice these are kind of like the whiskers that I draw. Woohoo! There it is, negative 5 pi over 4. Okay, so negative 1 pi over 4, 2 pi over 4, 3 pi over 4, 4, 5 pi over 4. Sweet. All right, so, then from here you can practice on your own. All right. Cool. So next up, let's continue with reference numbers. We're almost done. So this is, there's a few more exercises, but it'll go a little bit quicker from here. Okay, so what is a reference number? So it says, let t be a real number. The reference number associated, let's zoom in a tiny bit. The reference number, we're going to put a little tiny line on top. So the way we pronounce that is, I pronounce it as t bar. So if you ever see a little line on top in mathematics lingo, we call that t bar. So it is the shortest distance along the unit circle between the terminal point and the t-axis. Okay, what the heck does that mean? So let's do the following. So as always, let's draw a little quick unit circle. And let's draw a few examples here. So if this is the t, remember, literally it's the wet noodle, so it's that arc. Of course, I'm not going to draw it every single time. So then what is t bar? It is the shortest distance along the unit circle between the terminal point associated to t. So, okay, technically the t is the real number. The terminal point is the p here. Okay, now in this case, let me make my stick a little nicer. The terminal point t is the same thing as the reference number, because the shortest way to get to the x-axis is basically by following its own little path. Where it gets really interesting here is, let's say I am over here. And let's say that the t is actually, let's do it with colors. So t, remember, it starts all the way at 0. It has to wrap all the way around until I stop here. So t is this purple part. The point that I land at is over here. Let me maybe call this t1, p1, and then let's call the purple part t2 and p2, since they're different lengths. Now, here, the t2 is, again, it's actually quite a long piece, but the reference number is the shortest distance to get to the x-axis, which means, what is t bar? T bar, let's use maybe yellow, is actually this. This is the shortest distance from the terminal point, so I'm going to call it t2 bar. So what this allows us to do is basically, the whole point of introducing this notation is we really want to focus our attention on just these three whiskers. The pi over 4, which is this one in the middle, the pi over 6, which is this one, and the pi over 3. Once we've got basically that down, then we can kind of build all of the other whiskers based off of that by thinking of a reference number. Now, the key term isn't really so important, because you kind of, the more you practice this, the more that you just kind of do it subconsciously. But anyway, so that's our definition. Okay, so let's do this next example to really solidify it. Now, again, I encourage you, pause the video, see if you can do it on your own. All right. Let's zoom in a bit. Let me draw a couple of these unit circles, and I apologize, I'm going to get a little lazy and just do the minimal graph here. All right, 4 pi over 6. Where would we end up? Since we're doing let's do all the quick little whiskers for all of these. All right, so here's 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6 is right here. So let's label it in red. This is where we end up. So in terms of the four pi over 6, that is our wet noodle. What is our reference angle? Well, our reference angle is actually right here. Now, what would that be? So if you kind of remember the whiskers, if I go all the way to the top whisker, this is going to be pi over 3. So there is our reference number. Okay, let's do the next one. And this time, I'm going to actually remember to copy my little whisker plot. Let's do it for this one as well. Okay, so negative 5 pi over 4. Let's do our count. So negative pi over 4, negative 2 pi over 4, 3 pi over 4, 4 pi over 4, and 5 pi over 4. So we're going to end up right here. So negative 5 pi over 4 is this red distance, and that's where I end up. So our reference angle is the shortest distance to the x-axis. So this time the purple is going to be right here, and it's going to be pi over 4. So the reference angles actually always are a positive because it's a distance. So we're always going to measure them from the x-axis either up or down. It's always going to be a positive number. Okay, next, pi over 2. Oh, we know where that one is. That one is right here. There's our pi over 2. And this one's kind of tricky, because basically the shortest way to get to this is the same thing as pi over 2. And, you know, either way you go to the x-axis are both pi over 2. So it doesn't really matter which one you pick. So which way you draw it, it's basically its own reference angle. And sometimes that happens. All right, and now the trickiest one. So maybe if you didn't pause earlier, maybe try to pause it now. See if you can come up with an idea for this one. This one's tricky. So, 3. What the heck is 3? So 3 is 3, of course. Here's 3 fingers. But what is it in the context of what we're doing? Remember, it's a wet noodle. Now, if you have your calculator, what is approximately pi? 3.14159, blah, 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 blah. So remember, pi was exactly half of the circle. And 3 is, I don't know, somewhere over here. The key thing here is it's not on a whisker. Whiskers are the only locations we know the exact coordinates of x and y. So if we get something over here, well, you know, we don't know how to do the exact x and y coordinates. We'll talk later how we can do that, but for now, we just have to do it geometrically. Now, we're talking about reference angles. So I guess I've been using purple, but the reference angle is this little tiny measurement of length. Basically, I just have a little bit more to go to get to the x-axis. Now, if I want to write what this is as a number, remember the full half arc is pi. So I'm going to call it 3 bar for the reference number is actually going to be pi minus 3. So if you want an approximation to this, it's about 0.14. So kind of a challenge question, but it's always good to throw these in so that we really know, do I understand the concepts? And the answer is, of course, yes, you do. Great. Alrighty, so let's take quickly a look at this little how-to. So it says how to using reference numbers to find terminal points. This is a nice little summary here. Okay, so to find the terminal point P corresponding to a real number, use the steps. Find the reference number T bar, the terminal point Q corresponding to T bar, and then you basically do plus or minus A and B. So, you know, it doesn't look super nice to write up, but basically what this is saying is, once you know the coordinates, let me highlight it in green, for basically this little part here, quadrant 1, if you can just memorize the coordinates for this section, you can do all the other ones by just using the whisker trick, knowing what the reference angle is, and then comparing it and just adding pluses or minuses according to where you are in which quadrant. So that's kind of how to do that. Now, all right, almost done. I know today this lesson was a little bit long. They're going to go a little bit quicker moving forward. But again, it's so important that I really want to take my time, make sure everything is crystal clear so that you have a super solid foundation to build off of. Okay, cool. So let's do a few key points. A terminal point P of a reference number will always be in quadrant 1. Okay, I believe what I meant to say was, oh no, reference number was the T bar. Yeah, okay. Excuse me. Because the circumference of a circle is 2 pi, the terminal point determined by T will be the same as T plus 2 pi or T minus 2 pi. What is this saying? So that is kind of saying the following. So what if I add, let's say we're at pi over 4. What if I add to this, now let's use a different color. What color haven't I used yet? Bright green. What if I add 2 pi to this length? Because remember, I'm thinking of this as pi over 4 is from here to here. If I do add 2 pi, I have to add a full circle from where I started. That's why I'm using color here. Notice that starting at pi over 4, going all the way around one full circle, if I add 2 pi, I would land back to where I started. So the terminal point, the place where I land, is the same if I do pi over 4 or if I do pi over 4 plus 2 pi. Of course, they're different lengths, but in terms of where I land, I'll land at the same spot. Now, let me see, what is that? 9 pi over 4. So 9 pi over 4 is longer, but basically what that is one full turn plus the pi over 4. So that's the second bullet point. And then the last one is just basically a generalization. And this is one of these really key notes. We're going to use this a lot once we define the trig functions. But basically, if you add or subtract any multiple of 2 pi, that's the same thing as just doing one full turn. So you basically land back to where you started. Now, if you haven't seen this notation, this z here, it's z with a little extra stick, is our code name for, where do I write it? Let me write it here. This is how I write it by hand, z with a little extra stick. This is code for the integers. And if you remember what are the integers, this is going to be 0, plus or minus 1, plus or minus 2, plus or minus 3. Basically, plus or minus all of the whole numbers. All the whole numbers. Now, the real numbers have everything in between. The integers have only the whole number parts. Okay, and I'm actually going to leave this very last question here as a little challenge for you. So if you can figure it out, you can show me in class. I'll be very impressed. Okay, that's it for this lesson. Thank you so much for watching. I'll see you in the next video. Bye.